the heavy lifting for taking this and creating, when we're done, we'll be able to write an equation that fills in these dots here. Like so. We're going to fit an equation to that, and it's going to look something like this. B x minus c plus d. And you've got to be able to figure out all of these values. Well, to start with, instead of doing all these values by hand, we're going to do it using the sign regression function that's in Desmos. Okay, so Desmos, like I said, is going to do the heavy lifting. It's going to do all the calculating for us. And that's why we need a Desmos. Okay, and then we're going to learn how to find those things by hand. Okay. So when we're doing these equations, just a quick review before we type in the data and you've got to remember what these different things mean. Okay. Hey, can you get the lights, guys? Please, one of you open it. All right. So anything that is cyclic, this is called a scatter plot. And when the pattern seems like it's repeating, there's a good chance that you can fit it with a trig function, sine or cosine, right? And those trig functions are going to look like this. Now, if you remember, A stood for the amplitude, all right? The value B, that stood for the frequency. And the frequency was, that was the number of times, that was the number of cycles that you saw between 0 and 2 pi. So for example, if I drew a sine graph that looked like that, what's its B value? 2, because I can see there's 2 sine graphs. Here's one sine graph between those 2 points. And then I got another sine graph right here. Okay, and so together, this would be the frequency. 2 sine graphs, 2 cycles fit between 0 and 2 pi. That's what the B value is telling us. All right, the C value, that was the phase shift. So for that one, if I had a sine graph, like this, let's say. Okay, the phase shift over pi over 2, pi, 3 pi over 2, 2 pi. Okay, all a phase shift does is it slides this graph right and left. So that would be a phase shift of pi over 2 to the right. Okay, or if I moved it that way, that would be a phase shift of pi over 2 to the left. Okay, so our phase shift was sliding it right and left. It's the same as a horizontal shift. All right, and then finally the D value, that was the vertical shift. So that's what moved the graph. If I took this same graph here and I just slid it up or down, that's what the D value does. Okay, that was our vertical shift. Now in here is how to find those things by just looking at the data. We're going to find these things using Desmos to start with. Okay. All right. So yesterday we did this graph. We let this animation run and we looked at what your height was depending on the time. Okay, so, okay, bigger. All right, so this is what we did yesterday. Whoops, come on back. We're getting buffered right now. Sorry. So good on this. Okay, so over here on the right, we were following ourselves if we were on that blue dot right there. And we started at 3 o'clock. Okay. Vertical line. All right, so as we're going along, the intersection of these two, the curve, the vertical line and the horizontal line, describes what your height is. Okay, so at any point that I stop this, that gives me, this is the time here on the x-axis, and this is the height. So I'm at 30 meters above the ground. And it just keeps repeating over and over. Okay, so it's cyclic. So what we did was we took these little x's and we created a scatter plot. I had you do that first yesterday, and then you ran the graph and you found out, well, how accurate was my plot compared to the actual graph. And the coordinates of each one of these little points here is simply the time and the height. So on that Google sheet that I had you open, all right, all that is the time and the heights of this thing for 2 cycles. Okay, it takes 10 seconds for you to go all the way around on this particular Ferris wheel. So what I did was I collected all the data points here. I did the time and then I did the height, and that's what that Google sheet is that's attached to your classroom. So you open this thing up. Okay, you're going to see over here on the left the time, and then to the right of that, your height. So we started at 50 feet. This is 1 revolution up to 10 seconds right here. And then a second time around, here's your second revolution up to 20 seconds. Now, what we're going to do is plot that. So instead of having to copy it and type it in yourself, what I want you to do is click on those 2 columns, right, like I'm doing, drag it down like that, so it's highlighted, and then hit Control C, and that's going to copy it. And then you're going to go to your Desmos graph that you opened. And the cool thing is all you got to do is click right here and go Control V. And there's all that data. Okay, so let's do that first. Make sure everyone's got it typed in. Okay, so I'll come around and check. If you need help, let me know. So you shouldn't have to type it if you can just use the control cut, the cut. Got it? Right here. Fine. You have to be able to do this. Good. So you gotta go to the, don't try to type all these in. Go to the sheet that I opened. I gave you, and then highlight those things. Yep, there you go. Good. Yep. Got two on there. So yeah, just open up, not that one. Just go to our. Okay, copy and paste it into, you got it? There? All right. All right, so it's in there. Now what we want to do is we want to get Desmos to draw the graph that matches this. Okay, so here we go. It's so easy. Okay, type in. So everybody, you want to follow along. Is everyone ready? So I can type it in? All right, so we'll go one step at a time here. So I'm going to go Y1. Okay, and it should say you got 25 element list. There's 25 numbers under Y1. Okay, then in the upper left-hand corner of your keyboard, there's it's right next to the letter or the number 1. It's a little squiggle. It's called a tilde. Anybody need help finding that? It's a little, anytime you type that into Desmos, it'll do a curve fitting for you. You just got to tell it what curve you want it to look for. Do you want to look for a parabola curve or an exponential curve? In this case, we want to look for a sine curve. So what we're going to do now is we're going to type in the form here. Right there. Okay, after the Y, this says Y1, and then we got the squiggle. So right now, this looks like it's going to end up looking like this. This is going to be Y1, and this is a squiggle. And then when we do the X, we're going to make it X1. Now the square brackets, you can use parentheses, it doesn't matter. So it's going to look like this. Okay, I'm going to go A, that's my amplitude, sine, open the parenthesis, B, open another parenthesis, now type in X1, then minus C, now you got to close two parentheses, then plus D. And you should get a graph that runs pretty close to through all your points. Okay, and if you look down here, it tells you what the A is, what the value of B is, what the value of C is, and what the value of D is. So it calculated the amplitude, all right? It calculated the frequency, it calculated the phase shift, and it calculated the vertical shift. Now, this number right here, it tells you how good of a fit it is. I mean, just by looking at it, it's a pretty good fit, all right? The number that you look at to determine how well it fits is this number right here. So you're going to circle it, all right? The closer this is to 1, all right, this is called the correlation coefficient. And all that means is how well does the graph fit the data? Okay, the closer to 1 or -1 means a good fit. Good fit. So ours is pretty darn close to 1. It's 0.9994. That is really good fit. So when it's a good fit, then now you can use it to figure out questions about the whatever you're trying to model. All right. Any questions on what I did there? Now, right down underneath it, guys, all I did was take these and I just rounded them and I wrote out the equation. All right, so let's go ahead and do that. So click right below it. And now it's just y equals. Okay, take your A and round it to 2 decimals. Okay, so 49.53 sine parenthesis. Okay, now do your B value. All right, Colton, what's that going to be? Let's go to 4 decimal places. B. .63. What was the last one? 1. Yeah, because that 5 tells you to round the 0 up. Okay, then parenthesis. X minus, okay, Angel, round C to 3 places. 0.041. And then it even tells you you need 2 parentheses to close it. Okay, Caleb, how about D to 3 decimals? Yep. Now it put it in a different color. You can see how that color matches the black one. If I turn off the one we just typed in, there's the black one and there's the one that we just came up with. All right, now the other way, it all depends on how the question wants you to write out the equation. All right, so if the question asked me, what is the equation? And it said, I want it to be written out in this form. Okay, then that's your answer. That's your equation that models that set of data. Okay, now that's this one right here. It's y equals a sine B, and then you got all these parentheses, X minus C plus D. Okay, but if I said, hey, I don't want it like that, I want it like this. A sine BX minus C plus D. I want it to look like that. Like when you're doing this on Math Excel, it wants the equation to look like this, not the way that we did it. Well, it's really easy to do. All you're doing is, if you watch over here, guys, eyes up front, Jose, there you go, turn your head slightly to 1 o'clock, and you're good. All right, all I'm doing is I'm multiplying this times X, and multiplying this times that term, and I get those two. Now what I just did is I took this and I wrote it so that it looks like this equation. But even better yet, you can just have Desmos do it. So right underneath it, do another regression, but this time have the B times the X instead. So it'll look like this. It'll be Y, whoops, go Y1, squiggle, A sine parenthesis, now BX1 minus C plus D. And there it is. So you'll notice, guys, it looks different than the first one. It's just a different form, but you see how it covers up the exact same equation. Okay. So if I wrote out this equation now, y equals 49.53 sine B is 0.631 x minus C 0.026, close the parentheses, plus 50.337. See, they all look the same. So it's important, you got to realize that these aren't different equations, they're the same. If I turn this off, the red and the green are the same equation. Okay, it's just written out in a different form, that's all. These are exactly the same. All right, now here's the part that you got to understand. When it's written like the first one, this number is the phase shift, 0.041 to the right. That's the actual phase shift. When it's written in the second form, the 0.026 is not the phase shift. The phase shift is actually disguised when it's written like that. All right, so that's why we write it the other way, because it's easier to see the phase shift. So everybody look up here. Okay, that is the horizontal shift because of the way that we wrote it. Okay, now bottom one. This is not the horizontal shift. To get the horizontal shift on the bottom one, you've got to, you take this number, the horizontal shift is C divided by B. You don't have to do that when it's written like the top one, but you do on the bottom. Okay. All right, now using Desmos, okay, using Desmos, answer these two questions. How high above the ground is the rider at 22 seconds? How would you find that out? Where would you look on your graph? What's the height of the rider? Because that's not in the table. How could you use this graph to solve that? How high the rider is at 20? Here's 20 seconds, 21, 22. How could I figure out what this point is? How high is the rider at 22 seconds? Here's 22 seconds. I'm going to do something with finding that point. What do we get? I want you to click on it and show me that you can tell me what the height is at 22 seconds. Look at the graph right above 22 seconds. Got your graph written? Yeah, you got that. Now, do you have the table in there? Okay. Go to the Google. No, it's the one in your columns. Not the time. Start at 0. Yep. Now drag it down. There. Right. Graph. Just click and it go. Cool. All right, now let's see. So next to this, I would take that out. That guy. Sure. Let's do this. I just want to see your graph. What's that? Right up here. Right here. There you go. Yeah, Norris, one of these guys. Good. Okay, I want you to show me what's the height at 22 feet. How are you going to figure that out on the graph? Who knows? How'd you do that? We got 93 close. Going. Yep. Right. Want to get that exactly at 22? Yep. Yep. So we're not using any trig, guys. We're just clicking on the point. Okay. But it should work. Okay. Get rid of that. Just cut it. Cut it. Oh, here. get rid of all that. Well, go down and type in your equation. C, X, yeah, minus C. Okay. Okay. No, the I guess you got to get rid of those columns. One up. And highlight those columns. Now there it is. Showed up. Now find 22 seconds on the x-axis. Straight up. Exactly 22. Oh, yeah. Yep. There you go. How tall is it? There you go. Okay. Did I check yours? Okay, how about here? John, you're all set? Okay. You got it? Okay. How'd you get that done? Oh, you did that. Cool. Okay. Where would 22 seconds? Go up there. And, well, let's just do this. Find 22. Go down to XL, X-axis. Yeah, we did see that right there. And then the other one like 25. All right, now find 22. There you go. Yep. Find it, Colton. Yeah, boy, there you go. Perfect. You guys got it. See that? Now you're solving without using any trig. Okay, where's 22? 22. X-axis. Yep, going right there. Now go straight up. Where did it touch the grid? Oh, you had it. Well, if you zoom in a little, it's easy. You got it. How about here? You get it? Casey? Find it? Okay, gentlemen, Jordan? Have your equation? Okay, go to,
That's like, oh, like, the word, like all the words.
you see,
Like,
there you go.
Well, I obviously.
I'm sorry. Now, 520. I know, I saw that. I saw that. Oh, yeah. So once you get that at 22, that's like I'm fine tune. Zoom in, it's a little easier. Fine 22. You're almost there. That line. Oh my God, get back over the hump. Okay, now you guys found, you noticed that it was kind of hard to get exactly at 22. So I'll show you another way to do it. Here we go. Alt. Watch people, and it's hard. You click on here and you're trying to get exactly at 22. Okay, here's another way to do it. You're going to draw a vertical line. Okay, so a vertical line starts with the letter X. So just go down here and type in X equals. Hey, what are you packing up for already? God dang it, Colton. Equals. Sorry for you people at home. All right. Now I'm going to type in 22. You see how it drew a line at 22? Now, if I click on that point where it crosses, it's exactly the correct answer. You're not having to take this and go right and left, etc. Okay, that makes it a lot easier. All right, last part. Get rid of that. At what times are you 30 meters above the ground? So now you're looking for 30 on the y-axis. So you're going to go y equals 30. Now, every time, every place where it touches the graph, okay, this one doesn't make any sense because that would be negative 63 seconds. Can't be negative 63 seconds. So at 5.6 seconds, at 9.3 seconds, at 15.6 seconds, at 19.3 seconds, at 25.6 seconds, etc. So by drawing horizontal and vertical lines, we're solving this equation. If we draw a vertical or horizontal line, it tells us when we're at a particular height. When we draw a vertical line, it tells us the height at a particular time. Now, the reason why this is important is tomorrow we're going to be doing this, but with tides. And this curve tells you how deep the water is. So any ship that is going into a harbor has a book, or probably computer now, that has a graph just like this. And by them knowing what time it is, they can figure out how deep the water is and whether or not, if they go into the harbor, they'll run aground or not. If the water's not deep enough, then your boat sticks to the bottom. That's not a good thing. Okay, and that's what this picture is right here. We'll look more at it tomorrow, but the largest tides in the world are in Nova Scotia at this place called Fundy Point. And during the day, this is what the pier looks like. Every day it looks like, actually twice a day it looks like this. It almost looks like it's abandoned. 12 hours later, it looks like this. Look how far the water's gone back. You can't even see it all the way back to the mountain. It's just, this is dry land. Then 12 hours later, it looks like this. And then 12 hours later, it looks like that again. And it goes back twice every day, up and down like that. The water, and people think that the water's coming in and going out, and that's actually not what happens with tides. Okay, we say, oh, the tide's coming in or the tide's going out, but that's not really what's happening, and we'll explain that tomorrow. Well, I think people figured it out. If any of you have gone to the beach, you could walk way out at low tide, and then at high tide, the water's way high up on the beach. You go back and forth. Yeah, but it's pretty amazing. It's like 40 feet of water, 43 feet of water comes in and out twice a day. So we'll look at that tomorrow. Pretty cool. Yes. All right, for you people at home and our listeners in Madagascar, I'll see you tomorrow.